Hello everyone. So today we're going to go over section 5.6, independent events. Two events are independent if the knowledge of one event happening has no effect on the probability of the other one. So for example, tossing a coin and then tossing a coin again, those two outcomes will be independent of each other because the first outcome has no bearing on what's going to happen the second time. Whereas drawing a card from a deck of cards, if you remove a card from a deck of cards and you remove a second card, then those events will be dependent because depending on what you remove from the first draw, the probability in the deck of cards is going to change. All right, so usually, in order to do this kind of question, we want to look at whether the events that we're looking at are dependent or independent. So as I just stated, if two cards are selected from a well-shuffled deck of cards and the experiment is carried out without replacement, that is, if you take out a card, you don't put it back afterwards, and then we look at the first event as drawing a jack, and then the second event as drawing another jack, then those will be dependent events. Right? Because let's say if you remove a jack on the first drawing, then you only have 3 jacks left on the second drawing. Whereas if you didn't draw a jack on the first drawing, then you still have 4 jacks left for the second one. So the probability is dependent upon what you did the first try. And so for this kind of question, usually would use conditional probability, which is something that we looked at back in section 5.5. Okay, so now next up we have 2 cards are selected from a well-shuffled deck of cards again, but the experiment is carried out with replacement this time. That is, after we remove a card, we put it back. Then that will be independent. And finally, if you roll a fair die and then you toss a fair coin, first event is rolling an odd number on the die, and the second event is obtaining tails on the flip, then those are going to be independent events. Okay, so there's only one formula to kind of remember here, and it's not this because we're not looking at conditional probabilities today. So if we have two independent events and their probability are P of A and P of B respectively, then the probability that they both happen, so probability of A and B, is just equal to the product of the individual probabilities. A classic example of this is a person who is taking 2 courses. So it says here the probabilities that Emma will pass grade 12 math and grade 12 physics this semester are 0.85, so 85%, and 0.75, 75%, respectively. If these events are independent, we're going to determine the probability of the 4 different scenarios that could happen. Emma could either pass both, pass math, fail physics, pass physics, fail math, or fail both. So we can look at the 4 different cases here, starting with passing both. So that would be probability passing math and passing physics. Now, because they are independent, we can simply multiply the probabilities of each event. Of course, that will be 0.85 and 0.75 respectively, and the product of the two will be 0.6375. Okay, so what about passing math but not passing physics? Well, then we have probability of passing math, and then the complement of the probability of passing physics. Can simply write it as the product here. So probability of passing math times the probability of not passing physics here. Now, she's going to pass math 85% of the time, so 0.85. For the second part, if she passes physics 75% of the time, then she's going to fail physics 25% of the time. Okay, so good to make note of that. This is simply 1 minus 0.75. That's where that number comes from. And now we take the product. This will be 0.2125. So the probability of that scenario happening is 21.25%. Next up, the kind of the opposite would be for her to fail math but pass physics. Again, we're simply going to multiply the probabilities of the individual events, so failing math, passing physics. So that would be 0.15 times 0.75, and the product there will be 0.1125. And finally, the last scenario of interest is that Emma fails both courses, so that would be not passing math, not passing physics. So we can, again, multiply the probabilities together for the individual parts. That will be 0.15 times 0.25, and that is 0.0375, so the least likely of the four. Okay. So because these are the only four things that can happen, if you add all four of these probabilities together, you will get 1. Okay. And I know I said fail, pass, fail, but the way that the question is stated, it just asks if she will pass. So it doesn't account for scenarios that are like not fail but not exactly pass either. Those are all in the complement. So that's important to note. All right. Moving on. Same kind of question. On Friday, the probability that the Flyers win their game in Prince George is 5/9, and the probability that the Bears win their game in Smithers is 12 out of 17. Now, assuming independence, what's the probability that the Flyers win and then the Bears do not win? So in this case, we simply have to consider the probability that the Flyers win, which is 5/9, and the probability that the Bears don't win will be 1 minus 12 over 17, which is 5 out of 17. And again, because these two events are independent, we can simply multiply the probabilities together. So that will be probability of F times probability of not B. So that would be 5 out of 9 times 5 out of 17. So that's 25 out of 153. And in this case, if you just write that as a percent, that will be 16.3% rounded. Okay, so now in the next two examples, we're looking at the probabilities of events with more than one case. So far we only considered, let's say, in this example, we'd only look at one scenario out of the four that could happen, right? The four are they both win, or just the Flyers win, or just the Bears win, or they both don't win. In the last example that we looked at, we look at all four scenarios. So if you add, let's say, these three probabilities together, you'll have the probability of Emma passing at least one course. Okay? So thing is, you don't want to always have to add all these probabilities together. So there's a quick way of doing that in some cases. Let's look at the question here. It says all 1,000 tickets for a charity raffle have been sold and placed in the drum. There will be two draws. First draw for the grand prize. Second draw will be for the consolation prize. After each draw, the winning ticket will be returned to the drum, so it can be drawn again. So theoretically, one person can win both prizes. So Max bought 5 tickets out of the 1,000. Determine the probability, the 10th of a percent, that he will win at least one prize. So one way to do this question is to look at the probabilities of him winning both prizes, winning just the grand prize, winning just the consolation prize, and adding them together. A different way of doing this question, though, is to consider the following. That is, the complement of the event that he wins at least one prize is that he wins no prizes. So, what's the probability of him not winning the grand prize? Well, that would be win number 1, but not winning prize number 1. So there are 995 tickets that are not his out of 1,000. And likewise, for not winning prize number 2, or the consolation prize, is the same, 995 out of 1,000. Alright, so the important thing to note about how the complement works is that we have the probability of him winning at least one prize, so probability at least 1, is equal to 1 minus the complement, which we know is the probability of him winning no prizes. Okay, so we have 1 minus, and now we know the probability of this is not winning the first prize and not winning the second prize. Because those two events are independent, that's just the probability of not winning the first prize multiplied by the probability of Max not winning the second prize. We can substitute in the numbers that we have already, which is 995 over 1,000 times 995 over 1,000. And you can use calculator for some quick maths here. You'll get 0.009975, or just under 1%. So 0.9975%. Okay, so he has just under 1% chance of winning at least one prize. Okay, one more. Very similar question. Two darts player each throw independently one dart at the target. The probability of each player hitting the bullseye is 0.3 and 0.4 respectively. What is the probability that at least one of them hits the bullseye? Again, we're going to look at the complement. That will be both players missing. So really the probability of at least one is equal to 1 minus the probability that they both miss. So that will be 1 minus, well, the first player missing, so A, so not A, and not not B, players A and B respectively. So that would be, because they are independent, that will be the probability of A missing multiplied by the probability of B missing. And we can find those probabilities pretty easily. Just 1 minus 0.3 is 0.7. 1 minus 0.4 is 0.6. So we have 1 minus 0.7 times 0.6. And of course, the product there will be 0.42. So the difference, 0.58. And that is to say, 58% of the time, at least one of them is going to hit the bullseye. And that's it. So the key idea here is to find the complement, both of individual events and also of multiple cases. So that's it for today. Thank you for listening.